given the function f of x, how to find the power series representation of this function. So normally what we have given is some point A, so we want to expand the function f of x around the point A, and what we want to find is a representation of the function in the following form, so as a power series which is centered at A. Okay, so what you have given normally is the function is the number A, the f of x, and the task is to find the power series representation. Now, last time we saw already how to do this, or at least in principle we saw how to do this. So we saw that the natural candidate, because we saw last time that if such a representation exists, it must be unique. So and the power series is the Taylor series of f of x centered at A. So first what you have to do is you have to determine the Taylor series. Then the second step will be you have to find the radius of convergence of the Taylor series. And then the third step is to prove that such an inequality holds on an interval which might be a subinterval of the convergence interval of the Taylor series. So you have three steps. So the first step is determine the Taylor series of the function f of x. The second step, find the radius or interval, find the interval of convergence. Of the Taylor series. And the final step will be prove that there is that the Taylor series is identical. That the Taylor series is identical to the function, at least on some domain, which might be a subinterval, a proper subinterval of the interval of convergence. Okay, so prove that this equality here, so call this maybe star, holds on some interval which is normally a subinterval of the interval of convergence on a suitable interval. Okay, so in general, if you have given a function f of x and you have given a number a, that's what you have to do in order to find the power series representation of the function. Okay, we last time saw already one example. So we started with the function e to the x. So we are interested in finding a power series representation of the exponential function centered at the origin. In this case, as I explained last time, the Taylor series has a different name. It's called Maclaurin series. So what we have to do first is we have to find the Maclaurin series. It's easy. This is an easy task. So this is the Maclaurin series. Then secondly, we have to discuss the radius of convergence. But if this series is easy, the radius of convergence is infinity. Okay, and I haven't completed last time this program. So what is still left is this point here. So I still have to prove that at least on some subset or subinterval of the set of real numbers, okay, we have indeed that this series represents the function e to the x. Okay, so the third step is still left. This is what we want to do today. Now, last time I showed you already. Okay, in order to prove the third step here, okay, what we have to do is we have to look at the error. So in general, we have to look at the error here. We will define a polynomial, which we called last time the nth Taylor polynomial, where we just take the first n plus 1 terms of this series and add them up. So ai x minus a to the I. Okay, and what we have to show is that Tn, that the limit n tends to infinity of Tn of x is equal to f of x. This is what we have to show, but we can reformulate this by introducing the error Rn of x, which is just the difference between f of x and Tn of x. Okay, and then this relation here becomes okay. So what we have to prove is that the error is a function of x is 0 as n tends to infinity. So this is what we have to prove. So for instance, for this example here, okay, we have to prove that okay, if we define the error Rn of x as e to the x minus, and we take from the Maclaurin series the first n plus 1 terms, I from 0 to n, x to the I over I factorial, then we have to prove that this error here tends to 0 as n tends to infinity. Okay. For this, we will need suitable bounds for the error here. If we have suitable bounds, we might be able to prove something like this. Maybe I should stress once more. Okay, so it's not necessarily true that the error tends to 0 as n tends to infinity for all x in the interval of convergence of the Maclaurin series. It's not necessarily true. So this representation here, okay, might just hold on a subset, or on an interval which strictly contains the which is strictly contained in the interval of convergence. Okay. Now, in order to complete the last step, I showed you already last time that there is a very handy tool which gives us an estimate which will be good enough in most cases for the error Rn of x, and this is called Taylor's inequality. Okay, so what we need is we need estimates of the n plus first derivative of the function on some interval. So for all x with absolute value of x minus a is, let's say, smaller than some d. Okay, then if you have something like this, then the error can be bounded by, okay, but this constant here times and then the absolute value of x minus a to the n plus 1 over n plus 1 factorial. And this estimate will be true as well for all x satisfying x minus a smaller than d on this domain here. Now, actually, the proof of this is not very complicated. Okay, so let's maybe look at the proof of this because it's not very complicated, and the general proof is, if I remember correctly, is an exercise in our textbook. So let's just look at the case where n is equal to 1. This special case. So in this special case, we know that here from this the second derivative is bounded by m. And let's just take one part of this inequality, namely that this is smaller or equal than m for. And also here, I just discussed one case, namely the case where x is larger or equal than a and smaller. Here, actually, it doesn't matter, but just for convenience, let's write smaller or equal a plus d. Okay, so I just use this part here. Okay, now. You see that. So this is the assumption. Now you see that. Okay, we first have to look at we just start from here. Okay, and we take the integral on both sides. So if we start from here, we see that the integral from 0 to, now my notation is not very good, so maybe I change this to t here. So this is what we have. This is the assumption. So the integral from 0 to from a to x of this function here, dt. Okay. Now I need to assume that I'm in this case here, okay, because the x is larger or equal than a, so this integral here is not negative. So I can everything estimate. So I estimate this by m here, and I get this estimate here, and this holds for x which are between a and a plus d. Okay, but for this here we know that from the fundamental theorem of calculus, this will be equal to the first derivative at x minus the first derivative at a. Okay, so we get that the first derivative of x is smaller or equal than m x minus a. I should write this in the other. So the first derivative of f at a plus m times x minus a. Okay, and now I do the same once more. So I integrate this inequality once more. Then I get so from this original inequality, by just taking the integral on both sides, we get here a better. We get here an estimate for the first derivative, and if we take now the integral here on both sides, we will get a upper bound for the function f of x itself. Okay, so I guess I can delete. Okay, so again, I can replace dx by a t, and here I also replace x by t, and this will hold for t is larger or equal than a and smaller or equal than a plus d. And now I just once more take the integral on both sides. So f of x minus f of a, which is the integral from a to x, the derivative of f of t dt. This is the fundamental theorem of calculus. And because x is larger or equal, the x what I choose is larger or equal than a, so I can use the estimate is smaller or equal than, and I just plug here in. So what I get is the first derivative at a times x minus a plus m, and I have to integrate this one, but this one is easy. This is x minus a square half. Okay, so you see from this you overall get. Now I can delete this here. So you overall get that f of x is smaller or equal than f of a plus the derivative of f at a, x minus a, plus m times x minus a square half. Okay, and this has to hold for x larger or equal than a and smaller or equal than a plus d. Okay, and you see that what I wrote here is exactly t1 of x. Okay, you also see that t1 of x is nothing else but the tangent to the function at the point x is equal to a. So you see, if I subtract this from this inequality, what I get here is r1 of x. Okay. You see that r1 of x is smaller or equal than, and then you have m times x minus a square half. And this is true for x between a and a plus d. Okay, and similar you prove for the other cases, because the reason why I restrict to this case is because I have to be careful if I have given an inequality and I integrate this, because the direction might change. So if I do not have this case, I will get the same bound, but in the other direction, so larger or equal than minus m. But since I have here the absolute value, this will then prove this general case. But you see that if you plug in here n is equal to 1, okay, this proves already for this situation the inequality here for n is equal to 1. Okay, and this, but this is just for n is equal to 1, and if you have the general case, then what you do is you start from the m plus first derivative and take integration more times in order to overall n plus 1 times in order to end up with an estimate for the function. And what you get here is naturally the nth Taylor polynomial, and then you can subtract it as here, and you get an error bound there. Okay, so this shows you, okay, why this result is true here. As I said, the general case, if I remember correctly, is exercise in our textbook. Okay, but the important thing is for us, okay, how to apply this inequality in order to complete what I have done for e to the x so far. So in order to prove that the Maclaurin series really represents the e to the x, that e to the x is equal to this one. Okay, and first I prove it for all x which are bounded by some d. Okay, so if I have this restriction here, okay, so I have to look at the n plus first derivative of our function. So what is the n plus first derivative of our function? Okay, this will just be e to the x. Okay, so I get that the n plus first derivative is bounded. So for x in this closed interval, it's bounded by e to the d. Okay, so if I look at the, so this is my, I should say this is my claim. So if I look at the error, I can use here Taylor's inequality. So Taylor's inequality will tell me smaller or equal than this m here is e to the d. Okay, and then I have an absolute value of x to the n over n factorial. Okay, now I have still to understand. So n, I want to let n tend to infinity. So where does this go if n tends to infinity? I claim it's 0 as n tends to infinity. Who can tell me why? So this is a constant here. Okay, we do not have to care about this. So we just have to look at this here. So why does this sequence tend to, for every x, tend to 0 as n tends to infinity? The most easiest way to see this is just by pointing out that we have proved that the radius of convergence of this series is infinity. So this series converges for all x. Okay, but this means that the terms have to tend to 0 as n tends to infinity. And the same for the absolute value of the terms. Okay, so actually that this tends to 0 as n tends to infinity follows already from the convergence of this series here. Okay, so you see that the remainder goes to 0 as n tends to infinity, which means, okay, this relation indeed holds, okay, for all x where you have this assumption here. But the d is arbitrary. You can make it arbitrarily large, okay, which means this will hold for all x. Okay, but I have to note I have to work here with the d. Okay, the reason being that I need here a bound for the n plus first derivative. Okay, and just if I have this interval, I can bound this easily by e to the d, which is independent of x, and then I can argue like this. Okay, but eventually this will hold for all x because I can make the d as large as I wish. If I have a given x, I want to prove this, I just choose the d large enough such that this closed interval includes my given x. Okay, and this completes our three-step program. Okay, because now we have proved that actually this really holds for all x. You might have seen this relation already in high school, but I'm pretty sure that there was no proof in high school. This is one way to do it. Okay, looking at at least you need some bounds for the remainder. There are many different in the literature. There are many different bounds. This is the most easiest one, but there are also many others. We will see other situations where this bound does not seem to work. It's not good enough in order to prove that you have convergence. Okay, so remember, if you have given a function, you have given a and you want to figure out whether f of x has a power series representation at x is equal to a, what do you do? First, you determine the Taylor series. Second, you discuss the convergence behavior of the Taylor series. Third, you prove that the Taylor series on a suitable subinterval of the interval of convergence represents the function. 3 steps. We have already a power series representation of a couple of functions. 1 over 1 minus x was the most easiest one. Then we found also power series representation of the ln 1 minus x. We have already for the arctangent of x. We have now for the e to the x. So let's look at the next function, sine of x. Okay, and the point around which we want to have the power series representation again is 0, the origin. So we look at the Maclaurin series. So the first step is, okay, compute the Maclaurin series. For this we have to take the derivative of this function. So the first derivative of this function is cosine of x. The second derivative of this function is minus the sine of x. The third derivative of this function is minus cosine of x. And then we are back to the, so the fourth derivative of this function is again sine of x. And then the game starts over again. So for the first situation we get f of 0 is equal to 0. Then from here we get that the derivative of f at 0 is equal to 1. From here we get that the second derivative of f at 0 is equal to 0. From here we get that the third derivative of 0 is equal to minus 1. And from here we get that the fourth derivative at 0 is equal to 0, and this will go on like this. Okay, so we see that the Maclaurin series, okay, is given by, so we have the sum n from 0 to infinity. So the Maclaurin series once more is the nth derivative evaluated at 0 over n factorial x to the n. Okay, now you see in this case we just need the opt integers here, okay? Because for the even we have everywhere 0. So what we do is, okay, we write the same series, but now we replace here n by 2n plus 1, okay? And in this case we have here minus 1 to the n over 2n plus 1 factorial x to the 2n plus 1. Okay, so this will be the Maclaurin series for the function sine of x. So this is the first step. Determine the Maclaurin series. Okay, the second step is okay, find the interval of convergence of the Maclaurin series. Okay, so here, next we discuss the convergence behavior of this power series. Now here we have already many tools. So the tool which we are going to use is, we have different choices, but of course the tool which we are going to use here is the ratio test. So we have the absolute value, but I just don't write here the negative terms, because this will be, if you take the absolute value, will be 1 anyway. So what you have is x to the 2n plus 3 over, here you have an absolute value, over, and then 2n plus 3 factorial, divided by an, but an is absolute value of x to the 2n plus 1, and here you have 2n plus 1 factorial. So you can take out the absolute value of x squared, and you have the limit n tends to infinity. And you see here, most of the terms cancel out. What is left is 1 over 2n plus 3, 2n plus 2. But this here will tend to 0 as n tends to infinity. So what you get is 0, which means that the radius of convergence of this series equal to infinity as well. Okay, so this series is convergent for all x. And now we come to the third question. The third question is, okay, for which x does this series represent the function sine of x? Maclaurin series. And we know already that the radius of convergence, so with radius of convergence infinity. The third step is, okay, we have to prove, or we have to figure out for which x does this series, is this series equal to sine of x? Okay, so for this, once more, we use the Taylor's inequality in order to bound the error smaller equal than. Now, for this, we need a bound for the n plus first derivative of x. But this here is very easy in this case because you always have either plus minus sine or plus minus cosine. So the bound will be 1. So it's very easy in this case. And then you have absolute value of x minus to the n plus 1 over n plus 1 factorial. And again, this tends to 0 as n tends to infinity. Okay, which tells you, so from this you see that the Maclaurin series is equal to sine of x for all x. Okay, so also we also have now a power series representation for sine of x. All those power series representations are very important, and you will you don't have to memorize them, but you will naturally memorize them after some time because we will use them many times. Not in this lecture, but in other lectures, you will see them many times. Of course, you might be interested as well in expanding functions, because the examples we essentially saw so far are power series expansions centered at the origin, but you might be interested also in like centered at other points. For instance, let's say the point A is equal to 1. Okay, so you might be interested also in such a power series representation. So now we want to write e to the x as a series over n, and then coefficients an x minus 1 to the n. Okay, this is what we want to do. Of course, you could say, okay, I start with this one. Because I know already this one. Okay, so you can say I start with this one. I write x. I replace x by x minus 1 plus 1. Okay, and then I expand it. But then I have to collect the terms, and this is not very convenient. Okay, so I just use the usual approach, namely the 3 steps. So I start by first step. I look at the Taylor series. Okay, so f of x is equal. So all derivatives of our function are equal to e to the x. So from this we see that the nth derivative at 1 is just equal to e. Okay, so what is the Taylor series? The Taylor series is the series over n, and now I have e to the e over n factorial, and then I have x minus 1 to the n. Okay, so this is the Taylor series. Now, the second step would be, okay, discuss the convergence behavior. It's easy to figure out that the convergence behavior, so the radius of convergence equal to infinity, also in this case. And the third step is use Taylor's inequality, so as before. We can show that e to the x is equal to the sum n from 0 to infinity e over n factorial x minus 1 to the n, and this holds for all x as before. Okay, so here for the third step, you just use the same method of proof. You have to bound the derivative e to the x. For this, you first choose an interval which is the absolute value of x minus 1 is smaller or equal than d. Then you can bound e to the x by the nth derivative by e to the d plus 1 in this case. But the rest of the argument is just the same as you have seen before. And you can prove that, okay, this equality holds for all x. Okay, so we are missing actually one more function which is interesting for us, which is the cosine of x. Okay, now you can imagine for the cosine of x, you can do just the same as for the sine of x. Okay, but actually we have another method. the sine of x is equal to minus 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. Okay, so we know this already. And we know that, you remember we had a theorem which told us that if you have a power series, okay, then on the at least on the not necessarily on the interval of convergence without the endpoints, okay, we know that the sum function, okay, of the power series is a differentiable function, and we know that the derivative of this function has a power series representation as well, which is obtained by term differentiation. Okay, we have proved this before. So if you want to know the Maclaurin series for cosine of x, what you do is you just take the because we have proved this already for all x, you just take derivatives on both sides. So what you get here is cosine of x. Here the series n from 0 to infinity minus 1 to the n, and you can interchange differentiation and integration. This is and summation. I explained already earlier last time. This is not trivial. Okay, this is not a trivial step. You have to prove this, but we have a theorem, okay, which we saw last time, which allows us to do this. What you get then is okay, x to the 2n over 2n factorial, and this is already the Maclaurin series of this function, okay? Because the reason being because this expansion is unique, okay? So no matter how you derive, okay, a power series representation of a function centered at the origin, for instance, what you get is always the Maclaurin series, okay? So if you use our 3-step program, okay, where you first find the Maclaurin series, then discuss the radius of convergence and prove that the Maclaurin series is identical to the function, you will get the same result because once more, because power series representation is unique, okay? If you are asked to find the Maclaurin series representation of given functions, and the more you know already about functions, the easier it gets, because you just use what you already know, like here. And you use tools like differentiation and integration in order to derive corresponding power series representations. For instance, here it's also very easy for instance, this function. Okay, you have to imagine if you use our three-step program. Okay, you first have to derive from this for this function the nth derivative. Okay, you have to use the product rule. Okay, but the term is getting pretty messy if you do this. Okay, so it's much more easier just to point out. Okay, we know this already. You just multiply with x, and you take the x in, and that's it. Okay, so from this result, you immediately get that f of x has the power series representation n from 0 to infinity minus 1 to the n over n factorial over, sorry, just write this, minus 1 to the n, then x to the 2n plus 1 over 2n factorial. Okay, you would get the same result using our 3-step procedure. Okay, but you have to notice it's much more complicated. Okay, because if you want to find first the Maclaurin series, you have to take the nth derivative of this function. Okay, and this is more complicated. Okay, so once you know already a lot about power series representations, things are getting easier and easier. You just build on what you know already. Okay, so for instance, also this function, okay, is now easy. If you want to find a power series representation for this function, we just take the one for e to the x and plug in for x minus x squared. So we have series n from 0 to infinity, and then minus x squared to the n over n factorial. And we know that this here holds for all x, and also this here holds for all x. So this will be equal to minus 1 to the n x to the 2n over n factorial. Okay, and in particular, we can use this, and this is and this holds for all x. We can use this in order to compute the to get an expression for the antiderivative of this function. Okay, so I explained this already last time, but maybe it's time to look at another such example just to see why we are interested in obtaining power series representations of functions. So, for instance, once you have given this here, okay, you can easily find you can easily give an expression for the antiderivative of this function here. Okay, so what you do is, okay, you just plug this in, and we know that, and this is again a result. Okay, we have seen last time, if a function has a power series representation, okay, then its integral has a power series representation as well, and you get it by term integration. Okay, so from here you get this is the sum n from 0 to infinity minus 1 to the n x to the 2n plus 1 over, and then you have 2n plus 1 times n factorial. Plus a constant, of course. Okay. And this in some way solves the integration problem, okay, because this function, okay, if we can use this function. So for instance, if you have here the integral from 0 to 1, okay, then you will have here 1, and we can use this series in order to compute the answer, okay, up to how many digits we want, okay. Moreover, if you look at this, if you look x is equal to 1 in this case, okay, we have easy control of the error, okay, because this is an alternating series here, and the error, if we cut off, if we use the first n terms in order to approximate the value of this series, okay, it's just the first, it's just bounded by the first term you neglect, okay. But this here is 1 over 2n plus 1 n factorial tends to 0 very, very quickly as n tends to infinity. So it will be easy if you have this integral here. It will be very easy to, using this representation, it will be very easy to compute the value of an approximation for this integral up to as much digits as you want, 100, 200, no problem with this approximation. And this kind of solves this integration problem, something we could not solve last semester, okay? Because if you look at this function, it's to find an expression for the integral, as I explained last semester, it's not possible. Okay, so this is another. This would be an expression, but last semester you would have said, no, this I do not understand this kind of thing. Okay, but now since we accept also such objects, okay, we can give actually the antiderivative. Okay, and this is also a convenient tool in order to compute values. So this would be one application of representing functions as a power series. It makes it more convenient in some cases to compute integrals. Following example. If you look at the limit x tends to 0, sine of x minus x over x to the cube. Okay, so if you look at this limit, of course we all know how to compute it. What we observe is 0 over 0, so we use the L'Hopital, and that's it. Okay, so this would be one way. This is how we have done it last semester. And you see, if you use the L'Hopital, you have to actually use the L'Hopital 3 times because then the denominator will become 3 factorial, and for the numerator you will get 1. Okay, so you see that, or minus 1. You see that like this you can get the answer, okay? But of course, from last semester we understand the L'Hopital, but this kind of method does not give us a lot of insight why the limit, as for why the limit is really exists, okay? Now we have a much better answer. We can derive the same answer, okay, with a much better method in some sense, okay? Namely, what you do is, okay, we know that, okay, for sine of x, we know the Maclaurin series. Okay, so the Maclaurin series is x minus then x to the cube over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and so on, plus minus, and so on, minus x over x to the cube. Okay, and now you see that. You see now you really understand. Okay, why does the limit exist? Okay, because the reason simple because this guy here cancels with this guy. Okay, and now so this expression here you can divide it now by x to the cube. Okay, and it becomes minus 1 over 3 factorial plus x squared over 5 factorial minus x to the 4 over 7 factorial, and so on. And now you just plug in x is equal to 0, and what you get is minus 1 over 6. The same answer which you get by the L'Hopital, but the difference here, you should observe what is the difference. The difference is this tells you, okay, exactly why the limits exist. Okay, if you replace x by x squared, no, it does not exist. Okay, because well, x squared, it does exist as well. It's equal to 0. Okay, and you see this because of this. The main thing is this term here. Okay, so the term and this term. If you look at sine of x like this, you do not see this term. Okay. But this kind of tells you something which you have known already a long time, namely you can, you know already for a long time that you can replace sine of x by x if x is small, okay? And but now the Maclaurin series tells you, okay, what is the error if you do this, okay? Roughly this term here, and this term will give you this limit. There is one step here which needs explanation, namely this one. Why am I allowed to plug in the limit? This one, this step here needs explanation. You see why this step needs explanation? You see it, yes or no? This step here needs explanation. Why I'm just allowed to plug in x is equal to 0. Because this function is continuous. But why is this function continuous? This function is continuous, yes. But why is, I mean, if you have a function like this, if I give you a function like this here, why is this function continuous? Continuous is the right answer. But the question is, why is this function continuous? Because it's even differentiable. And this is, again, the theorem which we have seen last time. Because if you have convergence, okay, then this function is even differentiable. Okay, it's even differentiable an infinite number of times. Okay, and differentiable implies continuous. It's not completely trivial, this step here. Okay, you should observe that you can also say, okay, it's not true that this identity holds because you can because the limit of a sum is the sum of the limits. It's not true because you have here an infinite number of terms. Okay, it's not so easy. So kind of what you do is you wanna interchange the limit and the series. Okay, and for this you need assumptions. Now, if you have a power series, this works. But in general, if this is a more complicated function, okay, it's not true in general. You have to be careful if you interchange limits or a series. If you have to be careful if you interchange differentiation and a series. You have to be careful if you interchange integration and a series. Common mistake, which I see even in research papers very, very often. That's people assume that you can just interchange. Okay, so you see, you can do more such examples, and this will give you another reason. Okay, this is another strong argument why power series representation are important. I show you another example which is more at the heart of mathematics, which I find interesting, but this application has nothing to do with any application, real-world applications. Namely, okay, so we have okay, so this power series representation here is true for all x. So it's true for x is equal to to 1. So what you get is this expression for computing E, the number E, which we have introduced last semester in the first lecture. Now, this gives you also a good way to compute actually E, okay? And Euler observed this already, and Euler has used this in order to compute the first, I'm not sure, 10 digits or 20 digits of E. But now we know much more. We know billions of them, because you just plug this in a computer and let the computer run. So you will. But Euler computed the first 23 digits using this identity here, and now we know many billions of digits. Like in 2000, we knew 12 billion digits of E by more or less using this identity here. So you can just use this and write the computer program in order to compute many digits. And there are mathematicians who spend their whole life doing this. Now, another interesting application of this identity is maybe you have heard in high school that E is an irrational number, not a rational number, and this can be actually proved from this. So E is irrational, not in Q. Okay, so how to prove this? This is more for students who are interested in mathematics, because this doesn't have any applications, but it's a quick proof, and it's a nice proof from this identity here. This is one of the. There are many different proofs. This is one of them. So what you do in order to prove this, as you might guess, is okay. We assume it's not true, so we assume that E is rational. So assume that E is rational. Now, if E is rational, you can write it as P over N. And both of them must be larger than 0, because we know, or you can choose both of them larger than 0, because we know E is a number which is larger than 0. Okay, so where P and N. Now what you do is, okay, so this means that E minus, so what you do is you subtract the first n plus 1 terms of this series here. Okay. So this is the trick. So note that this n and this n is the same here. Okay. Now, if you do this, okay, because we know that this identity here holds, okay. So in particular, we see that this sequence, okay, is strictly increasing to E. Okay, it's getting larger and larger, and finally reaches E. So this must be larger than 0. Now, this is also equal to, okay, using this identity, the sum I from n plus 1 to infinity, 1 over I factorial. So let's maybe write out some of the terms. So we have 1 over n plus 1 factorial plus 1 over n plus 2 factorial plus, and we go on like this. Okay, so what we do is we take out 1 over n plus 1 factorial. Okay, and what is left is 1 plus 1 over n plus 2 plus, maybe I write one more, 1 over n plus 3 times n plus 2 plus, and we go on like this. Okay, so for this expression here, you see that this is smaller equal than, it's even, doesn't matter, smaller equal is, will do it. This is smaller equal than, now, what do? I replace this one by 2. I replace this one by 4, and so on. If I replace this one by 2, I make this larger. If I replace this one by 2 and this one by 2, I make everything larger, and so on. So you see that this is smaller equal than 1 plus 1/2 plus 1 over 2 square plus, and so on. Okay, which is smaller equal than. And if I compute this now, so the sum here is 1 over 1 minus 1/2, which is 2. So I have 2 over. Okay. So you see, we have this chain of inequalities. So we see that actually here for E, I can write P over N, because this is my assumption. So you see that, maybe to summarize this, you see that p over n minus the sum I from 0 to n 1 over I factorial is larger than 0 and smaller or equal than 2 over n plus 1 factorial. Now, wait a moment. I have to actually it's better to if you look once more at this inequality here. Actually, I can replace them smaller equal even by smaller. Okay, because like if you look at the first term, I make it really larger. Okay, so what I get is something which is really bigger. Okay, so I even have this here. Okay, now I multiply everything by n factorial. Okay, if I multiply everything by n factorial, what do I get? Here I get 0. Here I get p times n minus 1 factorial. And here what do I get? N factorial over I factorial. And which is smaller than 2 over n plus 1. Okay, now, so I multiplied everything by n factorial. So here times n factorial. Okay. Then I get this here. Now notice the following. Notice, okay, this is an integer. Okay. This here is an integer as well. Okay, because I goes from 0 to n, and this is what you get here. You sum just integers. So this here, what you see here, will be an integer. Okay, the n clearly is n is an integer. Okay, n is larger or equal than 1, so this will be smaller or equal than 1. Okay, so how many integers are there strictly between 0 and 1? No integer. Okay, so I have a contradiction to my assumption here. You see, you might have seen in high school the proof that square root of 2 is irrational. This is the proof that e is irrational. You might never have seen the proof that pi is irrational. Okay? And this is much more complicated. The reason why pi is much more complicated to prove that it's irrational, not easy to prove that pi is irrational, is the reason why it's easy here. So if we analyze this proof, why is this easy? The reason why this is easy is because I have this series expansion, and this here is a very good. This here, as n tends to infinity, tends to 0 very quickly. So this allows you. This is a very fast converging series representing E. This is the main reason why I so easily here get a contradiction. Okay, but for pi we do not have a good series which is diverging to. It's not so easy to find a good series which is converging very quickly to pi. That's the reason why for pi it's complicated to prove that pi is an irrational number. Okay, so you see this is another application, but this has nothing to do with any real-world applications. This is just for the joy of proving something like this. And this is maybe the most famous proof that I is irrational, already known. I guess maybe this proof is going back to Euler already, so already known a long time. You see the real surprise. When I saw this for the first time, the real surprise is that it's so easy. It's so easy to prove that E is irrational. Okay. In particular, if you know how hard it is to prove that pi is irrational, it's very surprising that when I saw this for the first time, I was amazed that it's so easy. But of course, you need the right idea. Okay, you have to start from this one. It's the right idea. And the complicated part about this proof is to come up with the idea. Okay, so how about a Maclaurin series expansion for the tangent? Now, of course, one way you could do this is you first find the Maclaurin series and so on. But if you want to find the Maclaurin series first, what you have to do is you have to differentiate this function n times, which doesn't seem to be a very convenient thing to do, because the expressions will get much more complicated. So what you actually want to do in order to find the Maclaurin series expansion is, you say, I know that this is the sine over the cosine, and I know already the Maclaurin series expansion for both of them, sine and cosine. So for sine we know it's x minus plus minus plus minus and so on. And for cosine we know it's minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus minus, and so on. Okay, and of course the question is, okay, is it not possible to find the Maclaurin series expansion of tangent of x just from those two here? And by using what we have done already in high school, namely we just divide here, like a polynomial, we just divide this one by this one. Okay, so use the long division algorithm. So I write here the first one like this, plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. And just take the whole thing and divide it by 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus minus, and so on. So here division. Now, if this would, because this here are power series, but if they would behave like polynomials, what I have to do is, okay, I have to first check, okay, how often is this contained in this one? So x times. So I have here x. Then I multiply everything. So I have x minus x to the cube over 2 factorial plus x to the 5th over 4 factorial minus x to the 7 over 6 factorial plus minus. And now I have to subtract this one from this one. So this one here cancels out. And for this one, for the x to the cube, what do I get? So x to the cube, I have minus 1 over 6 plus 1/2. And then I have other terms, plus or minus, plus minus, and so on. Okay, so you see that this term here is minus 1 over 3. Plus. So you see that the first term in the Maclaurin series is x to the cube, and I can use this in order to compute more terms. Okay. Now, if something like this is really true, I have to prove things before I'm doing this. Okay, because we know that if this is a polynomial, this is a polynomial. It's okay. Okay, we can use this long division in order to divide this one by this one. But those two are, strictly speaking, not polynomials. They are power series. Okay. It's not so clear that I'm really allowed to do this, okay? But you can rest assured there are results which tell us this is okay, okay? So in particular, it is possible to prove that if you have a power series which is convergent, and you have another power series which is also convergent, and you divide those two, what you need is that the denominator, the power series in the denominator, it's 0, is not equal to 0, of course. Then in this case, you can just do this, and what you get is the power series of this one. The radius of convergence might change. Okay, so if the radius of convergence of this one is, in this case, it's no problem. But if the radius of convergence of this one is like, let's say the interval from -1 to 1, and from this one is the interval from -2 to 2, then it's not so clear what is the radius of convergence of this one. Okay, so it might be even smaller than from -1 to 1. But there are results. So whenever you have already found the power series representation of two functions and you consider the quotient, you can use this method here, long division, in order to find the power series representation of this function here. Okay, this doesn't give here for the tangent of x. This doesn't give you something where you can write down the coefficients. Actually, they are quite complicated to write down. You can do the same for the secant, cosecant, and so on. And normally, for some of those, like the secant, the numbers which appear here as coefficients are well studied in mathematics, called the secant numbers. And but this sequence of numbers, it's not so easy to write down a nice expression for this sequence. But at least we get here a tool how to compute the first few terms of the Taylor series of the Maclaurin series expansion, and the same for the product. So whenever you have two functions, you multiply them. So you have two power series. You can just do it as you have done it for polynomials. That's okay. The reason behind this actually is always that inside the interval of convergence, we do not even have convergence, but absolute convergence. This is the reason why you are allowed to do this. If you have absolute convergence, then the behavior of a series is very similar to a sum. In particular, the behavior of a power series is about the same as polynomials. So they are really generalizations of polynomials. So for instance, if you have the function e to the x times sine of x, what you do is just plug in the power series for Maclaurin series. We know already for e to the x, the one for sine of x, and then you use the usual method which you have used already for polynomials in order to multiply them, and you will get the power series for the product of those two. Okay. So this allows us also to find the power series representation of tangent, also secant, cosecant, and other functions. How about the power series representation of the arcsine? We already computed the power series representation of the arctangent of x. So for the arctangent, how have we done it? We know that the arctangent of x is just the integral of dt over 1 plus t squared. And conveniently, we know a power series representation for this function. So we just integrate it, and we get a power series representation for the arctangent. That's the way we have found the power series representation of the arctangent. Now, for the arcsine, of course, you always have the general method, which is, OK, you take derivatives, and you write down the Maclaurin series, and so on and so forth. But the question is, OK, is there also such an easy way? Now, we know that the arcsine is the integral square root of 1 minus t squared. Okay, so what we need is a power series representation for this function here, but this we haven't discussed yet. Okay, so we have to look at functions which are of this form, 1 plus x to the alpha, where alpha is a real number. Okay, and we want to find a power series representation for such a function. Now, the special case where alpha is a positive integer is easy for us. This is something we have learned already in high school, also including 0. So in this case, OK, what we have to do is we use the binomial theorem. So we know that, OK, we can write this. Alpha choose k. I should choose here n from it's enough to alpha n, and then x to the n. Okay, so this we know already from high school. And actually, what you see here, okay, this is already. So what you see here, this is already the Maclaurin series of this function here. Okay, because once more, Maclaurin series expansion is unique. Okay, so what you see here is the Maclaurin series. Okay. It doesn't look like a series, okay, because it goes to alpha, okay, but it's no problem. You let it go to infinity, and you say alpha choose n is 0 if n is larger than alpha. Okay, then you really have, okay, so now we have found, in this case, we knew already. So for this special case, we knew already the Maclaurin series expansion from high school. Okay, now how about the general case? Now for the general case, we have to use our procedure. Okay, so we have to first to take derivatives, we have to find the Maclaurin series, we have to discuss the radius of convergence, and we have to prove that it will actually converge to this function. Okay, this was done by Newton. So Newton has generalized this relation here, this trivial relation, more or less trivial relation, to the case where alpha is a real number. Okay, so now, okay, so for this function, so in order to do this, we have to look at the derivatives. Okay, so the first derivative is alpha 1 plus x to the alpha minus 1. The second derivative is alpha times alpha minus 1, 1 plus x to the alpha minus 2. And you go on like this. So the nth derivative will be, okay, you have alpha times alpha minus 1, and so on. And the last one is alpha minus m plus 1. And then 1 plus x to the alpha minus n. Okay, so from here, from the first one, we get f of 0 equal to 1. Here from the second one, we get f of 0. So the derivative is equal to alpha. Here from this one, we get the second derivative of f at 0 is what? Is alpha times alpha minus 1. And from here, we get the nth derivative at 0 is alpha times alpha minus 1 and so on times alpha minus n plus 1. Okay, so the Maclaurin series n from 0 to infinity. So what we have here is alpha times alpha minus 1 and so on alpha minus n plus 1 over n factorial x to the n. Okay, so this is the first step. Find the Maclaurin series. This here, what you see here, this coefficient is normally called alpha choose n, which is a generalization of the binomial coefficient to the case where alpha is any real number defined by this here. Okay. Now, the next step is radius of convergence of this series here. So what we have to look at is the limit n tends to infinity. So n replaced by n plus 1. So what we have is alpha minus 1, and so on. So we have one term more. So n by n plus 1. So this one over n plus 1 factorial divided by this term here. So what we have is n factorial. Actually, everything the absolute value, I will write this at the end. And here alpha minus 1, and so on, alpha minus n plus 1. Okay, and we have here absolute value for everything. This is important here because alpha might be negative. Okay, so this is the limit n tends to infinity. Okay, and now we have here the absolute value of alpha minus n over. So here only this one is left, and here we have n plus 1. Okay, and you see easily this is 1. Okay, so you see that the radius of convergence is 1. So we see that this power series here so this or the Maclaurin series of our function has radius of convergence one. Okay, so the this series is convergent on the interval, at least inside the interval from -1 to 1. Okay, and now the third step is to prove that this series here, okay, at least at some sub-interval of the radius of convergence, okay, represents this function 1 plus x to the alpha. Now, for this situation, it's not so easy. Okay, by looking at the if we just use Taylor's inequality, it's not so easy. Now, maybe let's just we have 5 minutes, so let's ponder 5 minutes about why it's not so easy. Okay, so what we have to do is we have to bound the nth derivative. Okay, for the for Taylor's inequality, so we have to bound or the n plus first derivative. Okay, so you see more or less this here. We have to find a bound for this one. Okay, now you see that that if you assume that x is larger than 0 and smaller than 1, okay, so x is positive. In this case, if you bound this here, okay, so what you get is smaller equal than the absolute value of alpha minus 1, and so on, alpha minus n. So just this coefficient here, n replaced by n plus 1. And this here, if x is between 0 and 1, okay, because as n is large enough, the coefficient here will be negative. Okay, so and the x is between 0 and 1, so this will be bounded by 1. Okay, so for this case, this function will be bounded by 1. But you see the problem is if your x moves to -1, gets close to -1, because if x gets close to -1, so once more, if n is large enough, okay, because the alpha is fixed, when n is large enough, this coefficient here is negative. So you have here the function 1 over 1 plus x to some power. Okay, 1 over 1 plus x to some power. And if x moves to -1, okay, this function is getting unbounded. Okay, so it's kind of to find a good bound if x is negative is not so easy. Okay, but for this case, no problem. This bound. Okay, then from Taylor's inequality, what do we get? So from Taylor's inequality, we get, okay, so we have here absolute value of, so the bound times, and then the absolute value of x to the n plus 1 over n plus 1 factorial. Okay, so but actually this can be written as the absolute value of alpha choose n plus 1 x to the n plus 1. Okay. Now we have proved already. Because we know that the radius of convergence of this series is 1, so we have proved already convergence for all those x. Okay. Of this series, which implies that the terms tend to 0. So this tends to 0 as n tends to infinity. Doesn't look so easy, this term, okay, but we immediately get this from the convergence of the series. Okay. So this means that using the Taylor inequality for this range, okay, we have proved that this here, that the Maclaurin series represents the function for all x between 0 and 1. Okay. Here, for this range, the proof, because of this here, goes through. Okay. But if x is negative, not so easy. Okay. Indeed, it can be proved. It can be proved. That this representation holds indeed for all x in the interval of convergence. Okay. So you see here we have one case already, which we can handle by the Taylor's inequality. Okay. To handle the other case, okay, using with Taylor's inequality is not so easy. It's not possible, in fact. So you need other bounds. But in our textbook, this is chapter 11.11. If you look in our textbook, there is a very, very clever way to prove that this relation here holds for all x in this interval. Very, 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 very clever. You can take a look. You can take a look at it. It's one of the assignments there. So in this case, the exercise is there. So in this case, there is another way, completely different, which allows you to prove that this here holds, but much more clever. And this result, of course, is important. So this is called the binomial series. So this is an extension of the. So what we have here is, because you see that if alpha is an integer, here by definition the binomial coefficient will terminate. So if alpha is an integer, this will be a positive integer or non-negative integer. This will be 0 as n is larger than alpha. Okay. In other cases, you really have a series here, and this is a generalization of what you have called the binomial theorem in high school. Now for this function. Okay. Next time we will see some applications